So the question is, what determines the motion of galaxy? It can be galaxy cluster, it can be stars, but we choose a big scales because the effects of rapidly expansion is more visible by observing those objects in the big scales. This, for example, what we can indicate from this expansion is actually, or how we can understand that, how does this expansion occurs? How do we observe them, or what we indicate, right? So, the first essential reason is actually observing the redshifts, but these are not the redshifts. We are talking about the stars, but it is actually the cosmological redshifts that is dependent to the initial scale factor and also any given time and the scale factor of that given time. We will afterwards, of course, that the wavelengths of these redshifts are also dependent to the temperature of the universe. And the temperature is actually dependent to the scale factor, the rate of the expansion. So we are just discussing now, also just doing a revision of the previous videos, that we observed the nearby galaxies in the aim of write down the equations of the dynamics of them. So the first one is actually there's a gravitational field, right? Imagine that the galaxy cluster we are in and also observing around. Imagine that this cluster is so small. I mean, let us to embed it into one space, one point, okay? Like a spherical symmetry, okay? Every place is isotropic, homogeneous. In these conditions, we can apply the Gauss laws. So we can calculate the fields, right? There are two questions. What causes that field? I mean, the presence of the mass in given area or the sphere, doesn't matter what it is causing the potential energy around it. Because of the mass, there's a gravitational potential energy. We know this. Okay, so what produces this energy? The question is that. So we will apply that here is a given region in space. I think it doesn't write. Let us change it. Here is a given sphere and it includes galaxies inside of it. So many galaxies, okay? I don't know the number of galaxies per unit volume of it, but imagine that we have n number of galaxies inside of it. Doesn't matter. And they have variable masses, right? What contains actually, what they contain is actually stars. The stars and the presence of the stars in the galaxies are the mass of the galaxy. So we call, if we know the number of stars in the galaxy, if we know the material, interstellar material, interstellar dust, doesn't matter, planets, satellites, they are smaller, so we can neglect them instead of the stars. We can't neglect stars because they are massive. The galaxy's mass is actually the stars, right? So the galaxy that including so many stars inside of it, which can be the population 1, 2, or 3, or older stars and younger stars, doesn't matter. The number of them, if it is high enough, that which we can indicate that the galaxy's mass should be also enormous, right? So there are just galaxies inside of the sphere. So I assume that this sphere is embedded into one point, okay? So we will investigate it like this. So there's a potential, I mean there's a field around it. we can write down like this. Here, let's call this field, actually this field is gravitational potential energy. We can write down, why it doesn't write? Huh? Alright, right. Oh yeah, nice. Let's call phi. The phi stands for gravitational potential energy respect to the coordinates. And the coordinates can be u1, u sub 2, and u sub 3. Okay. Actually, u1, u2, and u3 can be defined by the metric. The metric we are working is important. It can be polar coordinates. It can be Schwarzschild metric. It can be GBL, sorry. Gauss-Bolyai-Lobachevsky metric. Can be Kruskal metric, or can be spherical coordinates, right? So I am not directly write down like x, I, and z, or maybe r, theta, and psi, something else, okay? Just writing down u1, u2, and u2. u sub I is better for pronunciation. U sub 3, these are just the coordinate distances, okay? So, we assumed in the previous videos, we choose a galaxy, and here is a total mass of m, and here is a total mass, actually the galaxy I choose, so as to understand the behavior of it in the given conditions of gravitational field, and also because of the expansion, because of the forming of those galaxies in the earlier times, it has the kinetical energy, right? It has spin around itself, and also the kinetical energy, and also the presence of the gravitational field that creates a potential energy between the system that it interacts, so there are forces on it. We will investigate these forces, but it's not easy. So first, permit me then to investigate what causes the force, the gravitational force. It is because the presence of mass in that embedded point, in embedded space or sphere, right? So, so let me write down again. I'm just removing them for free space. We know that it is something. I mean, this is a force that is proportional and also inverse proportional to the square root of distance between any chosen objects from the reference or initial coordinates, right? So this force can be described, I don't know what force it is, so just the thing I know is actually it is proportional 1 over r squared, right? If it is a gravitational force, then it must be some constant divided by r squared. So it is equals. If it is an electrostatic force, C constant can be bigger than 0 or smaller than 0. If it is 0, then there is no charge, there is no force, right? Because there is no potential around the charge. A test particle in this field cannot be exert force on it. So if the force is a gravitational force, then the C constant must be smaller than 0, because gravitational force is repulsive. It pulls everything to the center of the mass. Nothing can escape if there's no enough velocity to well, I think my brain is stopped. I don't know. To escape from this potential of gravitation, then it can be pulled together, and actually at the direction of radial coordinates, I mean the radial aspect, that's pointed toward the center of the mass. So they will come closer. The distance between them is just decreasing, right? It depends the sign of this given constant. For the gravitational constant, it is smaller than 0. And this is just what we intend to investigate. And desirously, we really want to investigate this case. So imagine here is a sphere, a galaxy cluster, including very types of galaxies, but let's call the total mass m. So we will apply, as I said, the Gauss laws of gravitation, right? For example, if there's an electric field in any given surface, doesn't matter place or space-time, the divergence of it, I mean the dot product of this function, which is respectively to the coordinates, must be rho u sub I, u sub 3, u sub 2, and u sub 3 divided by the permittivity of the space, right? Which means that the electric field caused by the presence of the charge in that given enclosed space or the coordinates. Okay? If there's no charge inside of this field, inside of this sphere, it can be a cylindric or maybe it can be a point, doesn't matter, then it shouldn't be any electric field, right? And actually this is differential form of it, so we can write down like the electric fields, the surface integral of this should be must be equal into this, right? And so we can write down like this, and also the closed integral of it, Q enclosed divided by the permittivity. This is differential form. This is integral form and differential form. Integral, differential, okay? Actually, this one is the Maxwell's law, right? The first law. So, where's my ruler? It's gone. So, if we can apply this to the gravitational forces, then we can write down this one. So, it must be some force which is proportional to the some constant divided by r squared, and just also that one. Gravitational force is equals g m divided by r squared. So if I measure that one divided by this is an acceleration, right? So let's call x double dot. And also it's a vector, so we must add that r hat, okay? So g is a acceleration of gravitation. Let me write down like this. Dot product dA. What is that? What it equals? The g is defined by the mass it's enclosed. Okay, so there's a field inside of the sphere, and it determines the motion of the particles around it. So here is a Gauss surface. We can call the distance or radius of this sphere r. So we can write down this equation directly. Why don't you write g? Okay, it's going to be finishing right now. G, here it is, g m over r squared, and dot product dA. What is the surface area of the sphere? Is actually 4 pi r squared, right? And actually it is directed or pointed in the radial direction. So we can write down this, and also we can calculate this closed integral. So also we have to write down that r hat is parallel to the surface vector, which is also normal vector. So we can keep going with this product. And as you can see from formulas, it is equals, they are removing. And also, I forgot the sign of it. Because of the gravitational forces, it has negative potential energy and the negative direction. Actually, the minus means the force attracts on the object at the opposite direction of its motion. Actually, it is pointed to the center, right? So the opposite direction of the radial coordinates. Actually, it depends what you assume for the positive x direction or y direction. It doesn't matter. It always pulls you up because it's a gravitational field. So it equals, here is a minus 4 pi g m, right? Here m becomes the mass that is enclosed in this given system. So we can write down enclosed, okay? Here is the Gauss law of gravitational field.